We're starting section 15.4, integration in polar, cylindrical, and spherical coordinates. Let's review cylindrical coordinates and spherical coordinates. Cylindrical coordinates is when you project a point from XYZ point into plane XY, and then from there you find the distance of the projected point. This would be X, Y, and 0. And the origin, that distance will give you R, and then the line segment that connects the projection to origin makes an angle with X, that would be theta. So R, theta, and Z is the same Z as you started with. Now, spherical coordinates. With spherical coordinates, you connect the point to the origin first. Then the angle made by the connection and z-axis, this angle is going to be phi. And the distance of the point itself from origin is going to be rho. Again, phi looks like this, rho looks like that. Now, how do we convert? Now, we still need a theta in there. So what you do is you realize that the relationship between z and rho and phi is z is equal to rho cosine phi. Then you project the point onto xy plane, and you realize that the distance of the projected point and origin is basically rho sine of phi. So R is going to be rho sine of phi. Now, when you find R, then you can find the relationship between R and X and Y. X is going to be R cosine theta, therefore X is equal to rho sine of phi cosine theta. Y is going to be R, the little r, that's little r, and times sine theta. So these are the conversion formulas that you will need. You need z, and you need x and y, which x and y come from r being rho sine phi. Let's look at how spherical coordinate sits there. See, this is the blue vector is the position vector of point A, and the angle you see right in here is going to be, this is actually the angle between z-axis and that position vector, and it's called phi. Then you see there's another angle after you project the point into xy plane. The connection between the projection point and origin, or the position vector for the projection point, and x-axis make another angle, we call that theta. And this vector, the length of this vector, the blue vector connecting the original point, it's the position vector of the original point, that's rho. And so that's how basically double integrals in polar coordinates. Recall the change of variable formula for double integrals. If g is the transformation that takes u and v to x and y, where x and y are functions of u and v, and g of s is equal to r, then the double integral over region R of f of x and y times the area element with respect to x and y is equal to the double integral with respect to s of f of x of u and v and y and u and v times the absolute value of the Jacobian, and that's with respect to the area element uv. Now we're thinking about the transformation from polar to rectangular coordinates. So u and v, the u, there is the u and v over here, and g takes them to x and y. U and v are here, r and theta, and g is defined by x equal to r cosine theta and y equal to r sine theta. The Jacobian is going to be, let's say, x with respect to r is cosine theta, then x with respect to theta is negative r sine theta, y with respect to cosine r is sine theta, y with respect to theta is r cosine theta. And that is going to give you r cosine squared theta minus plus r sine squared theta, which is r sine squared theta plus cosine squared theta, which is r. And so from now on, it's recommended that you memorize this part, that the Jacobian of the conversion from polar coordinates to xy plane is going to be r. And therefore, when you set up the double integral of f in Cartesian plane, it's going to be equal to the pre-image of r and the double integral over the pre-image of r and of f of r cosine theta, r sine theta, r dA with respect to r and theta. Here we're saying that r is the same as the region described in rectangular coordinates xy on the left and polar coordinates on the right. Okay, for purpose of memorization of this formula, what you want to, where we started was this. We even didn't go r and s. We said just remember r over here is described in Cartesian plane, here is described in the polar plane, and then we can simplify this a little bit further so we can memorize it a little better. And so basically you're taking a double integral, and if you have a double integral in xy plane, then you convert it to the polar plane by just plugging in r and theta for f, and then instead of dx dy, you will have r dr d theta. And so this is going to tell you that dA in xy plane, which is dx dy, is basically going to be replaced by r dr d theta. So again, dx dy is going to be replaced by r dr d theta. And so, yeah, the area element of in xy plane is r times the area element in dr and d theta in the polar plane. So now let's do an example. Here the double integral over d, which d is a disk of radius 2. Here's the disk of radius 2. And e to the power x squared plus y squared dA. If you remember, when you start integrating this one, what you see, the first thing that you see is if you set it up, and let's say there's set up, in either direction, you will have this issue that there is no elementary antiderivative. So that's one thing to remember, and there's no elementary antiderivative if you go with the xy plane. Now what do? First of all, it seems like we make the region easier if we go with polar, but also the integrand is going to be it's not possible to do in the xy plane. We cannot find the elementary function, and then it gets confusing, and then the next part will follow the same way. So now let's set up the double integral using the using the polar coordinates. First of all, the region is going to be r is between 0 and 2, and theta is between 0 and 2 pi. So I can set it up like that: 0 to 2 pi, 0 to 2. The inner one is dr d theta. Now, I converted dA to dr d theta. Do not forget to multiply by r. One thing to notice, by the way, when we were finding the Jacobian, we ended up with r. And we didn't have to put the absolute value around it because r is going to be positive. So for example, if you change the order, you end up with negative r, you have to put absolute value around it and get r. Now, one more step. What I haven't dealt with is this: e to the power x squared plus y squared. If I plug in r cosine theta, so r cosine theta to power 2 plus r sine theta to power 2. But r cosine theta to power 2 plus r sine theta to power 2, I know r squared factors, and I end up with sine squared plus cosine squared theta, sine squared theta plus cosine squared theta. So this is going to end up being 0 to 2 pi, 0 to 2, e to the power r squared r dr d theta. Now from here, I can actually find an elementary antiderivative, because I can use u to be r squared, du is going to be 2r dr, and then u is going to, if r is between 0 and 2, u is going to be between 0 and 4. So we get the outer function, the outer integral doesn't change. The inner integral becomes integral from 0 to 4 of e to u divided by 2 du. And then you integrate. I'm going to write it over here. 0 to 2 pi e to the u divided by 2, 0 to 4 d theta. And then you end up with 2 pi times e to the power 4 divided by 2 minus 1/2. Things to notice. So that integral did have an elementary antiderivative. And we found the antiderivative. But there were too complicated over here to find the elementary antiderivative. The next thing is that if you had forgotten the absolute value of the Jacobian over here, you would have gotten in trouble for taking the antiderivative. So make sure that you always put the Jacobian in there. Now, polar rectangles. In general, a region described in polar coordinates by r equal to r and theta, when r is between a and b and theta is between p and q, is called a polar rectangle. And then it corresponds to a section of an annulus let's say this red one is the annulus right here between the two circles, and it's just the section of that. And the green one is the annulus between these two circles, and so on and so forth. And so if you remember now, when you're going to basically infinitesimal dr and infinitesimal d theta, something to remember is that this arc length is just the radius times the theta, this radius times that theta. So you can assume that one length of it, as this polar rectangles become in xy plane become look like more flatter and flatter rectangles, and then one side is going to be r d theta, the other side is going to be dr, and so you get that the rectangle in polar coordinates in xy plane is going to look like one side is r d theta, the other side is dr. And so this is another explanation that the rescaling factor is going to be r. Let's do iClicker question 15.